We'll wait for 2 more minutes. Erase the previous topics that we have discussed. Check your notes and keep erasing. Yeah. So I think most of them have joined. We'll get started. So yesterday we discussed two topics, Lada. What were they? AC source connected across phasor diagram. AC source connected across resistor and capacitor. Now we'll see what will happen when you connect it across an inductor. Should we get started? So is there any doubt that you have from yesterday's discussion? Is it clear? Okay. Now let's write down the next topic, that is AC source connected across an inductor. Okay. Right. So when you take an AC source whose EMF is E naught sin omega t and you connect it across an inductor of inductance, you connect it. You want me to go up? Yes.
So they say the person who is conducting this initiative is not collaboration, not that person is available.
That's
They
fine.
asked me if they can call me.
Okay, good. Okay. Yes, when you connect this AC source across an inductor of length, inductance L, then what will happen is the current is going to start flowing. Right? The current that is going to flow through the inductor is alternating current. Is that right? When alternating current is flowing through the inductor, there is an alternating flux taking place through the inductor. Accept. So what is happening? Alternating current will create an alternating flux. So A flux means alternating flux. So alternating flux will create an EMF at the ends of this conductor according to Faraday's law. So what is Faraday's law stating? There is a change in flux taking place through a coil, then there is an EMF induced. Right? Is this happening? Yes. Okay. Now the question is, this EMF that is getting generated according to Lenz's law will do what? Will oppose the cause. Means this EMF is basically called as back EMF. Okay, this EMF is called as back EMF, and the reason being very simple, because it opposes the cause which is trying to produce it. And who's the cause which is producing it? It is the alternating source itself. Okay. Now what I can do is, if I calculate the net EMF, okay, if I calculate the net EMF, can I write it as E minus E? I'll write it as E minus E back is equal to 0. Why I wrote it as 0 is because when I say it is a purely inductive circuit, means only inductor is present, I can write that the net potential difference is equal to the current flowing through it multiplied with the resistance. Right? But what happens to the resistance? It becomes 0. Then I can say E minus E back is equal to 0. Right? Now from this, the important conclusion that we can draw is E will be equal to E back EMF. So what is E? E is the instantaneous voltage that we are giving using the alternating source. E back is the EMF that is getting generated across the ends of the inductor. When that is a scenario, I can write E is equal to, if you recollect the formula of back EMF from the 6th chapter, it says it is L into di divided by dt. I hope you remember this. Do you remember this? It's called L into di divided by dt. Now, what is our job? We need to find the current for the given input. What is going to be the output? So, a given input is E, and what is going to be the corresponding output? That is I. So for that, you will do di is equal to. Okay. Before that, can I write E as a function of t? it is E naught sine omega t, which is equal to L into dA divided by dt. Now, di, I will write it as E naught divided by L into sine omega t dt. Observe this. This is right. So this is a method you have been following since last year, right? So basically, just to give you an introduction, this kind of an equation where differential coefficients like dy by dx, dy by dt are there are called as differential equations. So whenever you need to solve a differential equation, you need to go with integration. So before you integrate, right, you need to separate the terms according to the variables and write it. For example, in this case, I separated t term separately and I separately. Means I'm trying to say I is a function of t. After that, I can go with integration. So this technique of separating the variables is called as variables separable. Okay, just for your information, and you learn about this in your math and 9th chapter in differential equations. So the name of this method, since last year you have been doing this. Kinematics, remember, A is equal to dV by dt. So you'll write dV is equal to A dt, and then you will start integrating. You separate the variables. Means dV is separated from dt. So since you're separating the variables, the method is called as variables separables. Okay. So coming back to physics, so I hope this equation is clear. dI is equal to E naught by L into sine omega t dt. So when I integrate on both the sides, can I write it as 1 minute? I'll write down all the steps again. See. So verify this is what you have written. So first you would have written E is equal to E back. So which is back EMF. E is equal to L into di divided by dt, which implies E naught sine omega t is equal to L into di divided by dt. So di will be equal to E naught divided by L into sine omega t dt. Integrating on both the sides, what do I get? I will be equal to E naught divided by L into integral of sinus by minus cos omega t divided by omega. Right. So this one you can write it as E naught divided by omega L into cos omega t with a minus sign. I didn't get it. Limits are not needed for this. Even if you take the limits, what will happen? 0. One minute. Even if you take the limits, right hand side, you will take it as 0. So when time was 0, the current induced was 0. When time is t, the current induced would be I. It's the same thing. Okay, but yeah, see, one more thing. I just wait, cut the limits. I'll give you another way. See, since you're doing indefinite integration, okay, you need to add a constant. If suppose you're taking indefinite integration, means without the limit, you're going to add the constant. So if suppose you add the constant, okay, let's say this scenario is coming, then what you can say is you're applying the voltage, right? So the applied voltage is a function of what? It's a function of sine. So for a sinusoidal wave in a complete cycle, what is going to be the average of it? For a sinusoidal wave in a complete cycle, I already told this point. That is why the average value of current over a complete cycle came out to be 0. So that's what is given. We expect the current also to be sinusoidal. Thus the average value of current must be 0 over a time period. Now, If you do the same thing with respect to cos also, you'll get the same 0. And that is why in this scenario, what will happen is constant is also ignored. Okay. So it is because we take the average value in this scenario. There are two things that you need to observe. Here I wrote an expression, you remember? E minus E back is equal to I into R. Why did I write I into R? Because actually I applied Kirchhoff's law. So E minus E back is equal to I into R, but I took R to be 0. But if you see, inductor is also made of some conductor only. It's some wire that is wound, right? Because it is allowing the current to pass through it. So you cannot ideally say that the current value, the resistance is going to be 0. But we take it to be 0, assuming it has to be a purely inductive circuit. That's what the theory says. But 99.9% only it can be accurate. 0.01% you will have an error. So that is one point to be noted. And the second is when you're taking the average value, the constant can be ignored in this scenario. So you directly go with this parameter. So that is why I didn't write it. Okay. So I will be equal to E naught divided by omega L into minus cos omega t. Now, I will be equal to this E naught divided by omega L. You can write it as I naught. Again, we discussed about this cos yesterday. Whenever you have cos, if you want to write it in terms of sine, what can you write it? You can write sine pi by 2 minus omega t or sine of pi by 2 plus omega t. In yesterday's scenario, you wrote it as, in capacitor, we wrote it as pi by 2 plus omega t. But in this scenario, you will write pi by 2 minus omega t because you have a minus sign outside. Now, what will happen when this minus sign is sent inside? The properties of trigonometry says sine of minus theta is minus sine theta. Is that right? So when I push this minus sign inside, I will be equal to I naught into sine of omega t minus pi by 2. So I have still maintained the same thing. I have made the omega t parameter to be the same as that of the input value. As a result of which, what can you conclude from this? What can you conclude from this? You can say that the current is, the capacitor is moved, you will understand what I'm trying to say. For a capacitor, what did we say? Current leads the voltage by pi by 2. Why did we write leads? Because if you had omega t plus pi by 2. Here what is happening? The current lags the voltage by pi by 2. So when you take that to be the scenario, now see, I'm going to draw a phasor diagram where if I take this to be the EMF, okay. So when I drop a perpendicular onto the y-axis, this will be E naught sine omega t. Then what will happen to I naught? I. It will be in the fourth quadrant like this. Okay. So this value is omega t. This whole angle is pi by 2, right? So what will happen is this angle will be omega t minus pi by 2. So when you drop a perpendicular here, this will be I naught sine of omega t minus pi by 2.
Sir,
Yeah, tell me.
sir, can you explain how minus cos omega t is converting to sine omega t minus pi by 2?
See, instead of omega t, I'm writing it as theta. Okay. Minus cos theta is equal to minus sine of pi by 2 minus theta. Accepted? Push the minus sign inside, it becomes sine of theta minus pi by 2. Now is it clear?
Yes, sir.
Yes. So this is how the phasor diagram looks like. Right? Now we will try to draw the graph for it. EMF and current. This is the value of EMF. Now what can you say about the current? Current lags the voltage by pi by 2. Means when the EMF is maximum, current will be least. So it starts here. So this is the graph for E naught sine omega t, and this is the graph for I naught sine of omega t minus pi by 2. Is that clear? Okay. So what statements can you write here? Current lags the voltage by pi by 2, or voltage leads the current by pi by 2. They both mean the same. Current lags the voltage by pi by 2, or voltage leads the current by pi by 2. Okay. Now the next point that we need to notice. If you see the expression for I wrote I is equal to I naught into sine of omega t minus pi by 2. But what did I write I naught as? E naught divided by omega L. Right. So what is this omega L called as? If you revisit capacitor, you will get an idea for what. So it is called, it's not resistance. There it is capacitive reactance. Here it will be, this omega L is called as inductive reactance, and it is given by the symbol XL. Is that clear? It is given by the symbol XL, and you can write XL is equal to 2 pi f into L, because omega is 2 pi f. So when you draw the variation of XL versus f, then how will it look like? It will be a graph that is passing through the origin. Is it clear? So there is a graph for variation of XL as a function of frequency. Slope is 2 pi L. Correct. Any doubt?
Sir, can you scroll up one?
Sure. Tell me that. Variation of XL versus frequency. XL na inductive reactance. versus F is frequency. Yeah. This is okay?
Yes. Yes, sir.
Clear? Shall we proceed?
Sir, can you tell why E minus C backward was 0 in starting? Sir,
Because resistance is 0. I wrote it as I into R, but
yes,
R is
sir.
0 because it's a purely inductive circuit. R is considered to
Okay,
be 0
sir.
and R you put
Okay,
this as 0. Okay.
Yes, sir.
Yeah. Now, with this knowledge, we will see what happens when an AC source is connected across a series RC circuit. So, when you connect an AC source across a series RC circuit, what is going to happen? R and C are connected in series, and the whole connection is connected across an EMF source like this. So, which is E naught sine omega t. So, this is going to be R, this is going to be C. Okay. Now, observe, if I is the current that is supplied by the EMF source, then the same value of current should pass through R and C, except why? Because they are in series. Since R and C are in series, so write it down, since R and C are in series, current through resistor and capacitor will be the same. So what current are we talking about? The alternating current. Write it down. Right. Since R and C are in series, the current through resistor and capacitor are the same. Okay. Now, this is where I want you to concentrate. Listen. If I say current through the resistor is I, then can I say that the current through the capacitor is also I, etc. Right? Now, if the current through the resistor is I, then how is voltage across the resistor related to the current? For that, you need to revisit the phasor diagram for AC source connected across a purely resistive circuit. That is the first one. How was EMF and current in the case of a resistor? They both are in same phase. So, can I say VR is also in the same? Means I is in the horizontal direction, VR will also be in the same direction because they both are in the same phase. Now, what about the current across the capacitor and the voltage across the capacitor? So, in the case of capacitor, current leads the voltage by, they are not actually, you cannot say out of phase up 180 degrees. Okay. So they have a phase difference of 90 degrees. So which one is leading? Current is leading. So can I say voltage will be like this? So if I draw something downwards, I am saying that is lagging. So what we have done in this scenario is we have exactly done the reverse process of the one we did in phasor diagram for capacitor. So first we fix the direction of current and then we found out what is the direction of voltage across each device. Is that right? Now, for this whole combination, if I take the phasor diagram, so when I say phasor diagram is mainly used to draw the quantities which are represented as sinusoidal functions. So here there are two quantities. One is VR. So if I take VR to be like this, then how is VC with respect to VR?
90 degrees.
90 degrees in which direction? Is it leading or lagging? It is lagging. In the
Lagging.
sense, VC will be here. Are you able to understand what I'm trying to say? Means, if this is VR, if this is VC, look at the way they both are. Right? So VR and VC are 90 degrees out of phase. So the resultant of these two will be V effective, which is given by the expression V effective is equal to root of VR square plus VC square. This is using the parallelogram law of vectors. So this is using the parallelogram law of vectors. And for V effective, what I will write is, I will write I into a parameter called Z. What is that Z? I will explain it later. So I write it as I into Z will be equal to square root of VR. I can write it as IR square plus VC square. I can write it as I XC square. Except, did you understand what I did? VR is equal to IR, VC is equal to I into its equivalent resistance, that is XC. Okay. So IZ will be equal to I into root of R square plus XC square. I and I will get cancelled. From this, what can I say? Z will be equal to square root of R square plus XC square. Okay. Now I'll tell you what the Z means. The Z is called as impedance. So there will be three terms that we have seen. One is resistance, second is reactance, and the third is impedance. So when do we use the word resistance? When it is a purely resistive circuit. Means if the whole circuit consists only of resistors connected across an AC source, you call it as a resistive circuit. If there is inductor or capacitor connected across the AC source, you call it as a reactive circuit. Reactive circuit because they offer reactances. Whereas if it is a combination of resistive and reactive elements, you call it as impedance. So impedance is used only when you have resistor and some either capacitor or inductor present. So impedance is also resistance only, but it is the equivalent resistance offered by the resistor and the capacitor put together. And that value is given as root of R square plus XC square. See, if you can think of this fact. Had there been two resistors like this, R1 and R2, if they both were connected in series, what would have been the equivalent resistance? It would have been R1 plus R2. It's as simple as that. But here we can't do it. I didn't add R plus XC. Observe. Like how you wrote R1 plus R2. R1 in this case is R. R2 I can replace it with XC. I didn't write it as R plus XC. Rather, we wrote it as root of R square plus XC square. That is the point you have to note here. You are not able to do it because there are phase angles involved in them. So here you're talking about devices having currents leading and backing. So, and also it is a combination of resistive and reactive elements. Is that point clear? So you should not write it like this. Rather, this is the right way. Am I clear with this point? Is it getting registered? Yes. So Z is equal to root of R square plus XC square. Similarly, if I take this whole circuit diagram again, if I take the whole circuit diagram again, and if I say this is phi, where phi is the phase difference between whom? V effective and VR, then I can write tan phi is equal to VC divided by VR. If you recollect from vectors, if this angle is phi, okay, so with respect to phi, the opposite point is VC, and with respect to phi, the adjacent point is VR. So tan phi will be equal to VC divided by VR. So VC is I into XC, VR is I into R, I and I will get cancelled, you will get XC divided by R. So phi will be equal to tan inverse of XC divided by R. So remember this expression, okay? Okay. So tan phi is equal to this thing. Then what will cos phi be equal to? Cos phi enna varum? VR divided by V effective. VR divided by V effective would have been the answer. So it would have been IR divided by I into root of R square plus XC square. I and I will get cancelled. Then this will give you R divided by root of R square plus XC square. And this cos phi is an important term which is called as power factor. Remember this term, okay? It's called power factor. It's coming. So I'll scroll it down just a minute. Are you done copying it? Okay. So cos phi will be equal to R divided by root of R square plus XC square, or just R by Z. Have this in your mind. This term is very important. We'll have it in the future discussion. Cos phi is called as power factor. Is this point clear? Right. Now, can I trust you and give you a task? Yeah. I'll give you 5 minutes time. Do this. AC source connected across a series R and L circuit. So this is the task. AC source connected across a series R and L circuit. So what you have here, resistor and inductor connected in series across an AC source. R and L. Is this point clear, guys? Yes? Draw the phasor diagram. Okay. So no need of graph for this. Draw the phasor diagram, find the effective value. It is exactly the same logic that we use for capacitor. There will only be a small change. If you can identify that, you have understood more than 50% of the chapter. How many of you got the answer? What is the value of impedance? Root of? Let's check your notes, correct? Yours is also right. R square plus XC square, yellow, XL square. The thing is, so this is I and this is VR, correct? If this is I, then this will be VL. Why? Because in the case of an inductor, voltage leads the current by pi by 2. So when you combine these two and draw it on the same graph, this is VR, then this will be VL. So how will V effective be? V effective will be in this way, and this angle you can take it as phi. So phi is always taken with respect to effective value and resistor. Okay. So V effective will be equal to how much? Root of VR square plus VL square. What is V effective? It will be I into Z will be equal to root of IR the whole square plus I into XL the whole square. We come there. Right. So from here you can write Z is equal to root of R square plus XL square. I hope this point is clear. Now the next point is about tan phi. So what will tan phi be equal to? Tan phi will be equal to VL divided by VR. So it will be I into XL divided by I into R. Both will get cancelled. So tan phi will be equal to XL divided by R. So when that is the case, what will you get cos phi as? R by root of R square plus XL square. So you will get R divided by Z. So if you observe, in previous scenario and this scenario, cos phi is common. Tan phi is only varying. Right? So that is why the cos phi here also is called as power factor. Okay. Is there anyone having doubt in this? Is there any step that is not clear? Now, the next point is AC source connected across a series RLC circuit. Right. Can you guys try this also? I'll give you 2 minutes time. Try it out. So it's a combination of RC and RL put together. Is that clear? This is I, this is VR, this I, this is VR. How many times? So this is VR. If this is I, this will be VC, right? So all the three will appear in the same graph. This is VR. This is VR. This is VC. So VR, VL, and VC. Now VR and VL are having a phase difference of 90 degrees. VR and VC have a phase difference of, which one is VL? So VR and VL have phase difference of 90. VR and VC also have a phase difference of 90, but VL and VC have a phase difference of 180 degrees, right? Now, I can think of making this VC come this side. Then what will happen to it? It will become minus VC. Is it clear? So 1 minute. I'll draw it as a separate diagram. So if I repeat the phasor diagram again, this is VR. This is VL. This is VC. Okay. So we can make this VC in this way. And I can write it as minus VC. Okay. Now what will be the effective value here? Can I say V effective is equal to root of VR square plus VL minus VC the whole square? Can I say that? Right? So then V effective, I can write it as I into Z is equal to root of I into R the whole square plus I into XL minus I into XC the whole square. Any doubt? Those who are online, any doubt? Is there any step that is not clear? Yeah, please.
Sir,
Tell me.
sir, why not VR square plus VL square minus VC?
Okay, VL minus VC is one vector. This whole thing is VL minus VC. So when you write it, you will not write it as VL minus VC separate.
Okay.
That's how vectors work. Yeah, tell me. Why unnecessary? You will take the effective of that and again effective of that. It's unnecessary. When you have an operation called as subtraction of vectors, why do you want to complicate? Okay. Maybe you will get an expression which you will not even see, but that when you apply in problems, you will get the same answer. But the equation that you will derive, right, will be so complicated. Okay. So if I take I into Z will be equal to I into root of R square plus XL minus XC the whole square. I and I are gone. Z will be equal to root of R square plus XL minus XC the whole square. Is that right? So this is what is going to be the impedance of this circuit. Now, again, I want to write Ethan, any doubt? Your okay. You have any doubt? So tan phi is equal to, what is tan phi? VL minus VC divided by VR. Correct? VL minus VC divided by VR. So VL I can write it as I into XL. My VC I can write it as I into XC divided by I into R. If I take that I outside, I'll have XL minus XC divided by R is what is tan phi. Whereas if you write after tan, what will you write generally? Cos. If you try to write the expression for cos phi, then cos phi is still going to be R divided by Z. Okay, and in this case also it is called as power factor. So I've been telling this power factor, right? Can you guess what would be the range of the power factor? It will be between 0 to 1. Negative values we generally ignore. So it will be between 0 to 1. So this power factor is one such important parameter that we need to understand, and it has a significance also. Have you ever seen the meters that are the power meters that are there outside your house? You know how you get the EB bill? Every month they come, you will have a card outside, they will write on it and go. Have you ever seen that? Maybe that will happen during your school hours, but during your holidays, have you ever observed? Current bill every they will write and go. No, they'll see the reading in a meter, right? EB card, that white color, it be in the form of a chart. They will write down the reading. So, reading, what reading are they going to write? Suppose they write 25,632. What unit is that? That's something a part of your syllabus.
Kilowatt.
It is kilowatt hour. 10th standard commercial unit of energy. So, unit is the layman language, but if you see the technical name inside, it is kilowatt hour. Somebody online also told. What did you say?
Yes, sir. Kilowatt.
It is kilowatt.
Yes, sir.
Right. Similarly, there are two kinds of meters that you will have. One is called as an analog meter, and the second is called as a digital meter. So, analog meter, you will have a small wheel which will be revolving. I'm not sure if you've seen that. Yes or no? No. Okay, I'll show it. Wait. I'll tell you why I'm telling you all this once. Just a minute. Okay. Sir, you have to see. Here we come. Wait for it. You're able to see this reading. Reading Malabar. That is what is kilowatt hour. And this is the wheel I'm trying to talk about. Yeah. You're able to see a spinning wheel kind of thing, right? So it keeps revolving actually. This works on the principle of your electromagnetic induction. Eddy currents, it works on that principle. So based on how it is revolving, the reading here will keep changing. That last digit is there, no, it keeps rolling inside. That roll at the number 8, 9, then it will start increasing the tens place, hundreds place. Okay, but that's not the concern here. When you look at a digital meter, right? Digital meter, let's see what is happening. You have that voltage. I spoke about the voltage. 234 volt is what you are receiving at your house. 220 to 240 volt. So what is that value actually? It is RMS. Okay, and you have the current also, right? Power irukku, and the frequency that we get in India is 50 hertz. Actually, there is an experiment itself in your lab that you will do this year, where you need to find the frequency of the AC source that we are using. For that, you use a device called a sonometer. You have seen sonometer. Adnala or paper, so you will have it with the tuning fork. Last year, we didn't go to lab. No? You didn't go to lab last year, right? You would have missed it. So, a long or device on which you will have a string. That string, on the string, you will keep a paper and you will hit the tuning fork and take it close to it. You should not touch the string. The paper will also start vibrate and it suddenly fall down. And it is happening because of an effect called as resonance. That will be the next topic we'll discuss. Resonance and variability. I've taught this last week. So resonance effect, something using a force method, you're creating a frequency that matches with the surrounding. See, if I have to give you an example, I'm not sure if you have experienced it. See, generally when you want to cross road, okay, it's a crowded place. Let's say you're standing on a road on a footpath. Okay, you're trying to cross the road. Let's say there is a heavy vehicle coming from the right of you. When it crosses you, whenever you're closer to the bridge, right, have you ever observed a vibration? Have you ever observed the place where you're standing, you have a small kind of vibration? Have you ever experienced it? Yes, no. You have not. No. Next time, observe it. That effect is also called as resonance. So the vehicle is there, but you're feeling the vibration here. So it is actually getting transmitted. So that frequency gets transmitted here. We call it as resonance effect. Okay. So, so your meter itself, if you have a digital meter at your house, you can actually have a look at it. One is you can see the voltage, you can see the amount of current that is being drawn by the devices put together. And last one, that power factor. That is the cost rate that I'm trying to talk about. And generally, that power factor will be a value somewhere varying between 0 and 1. It has a significance. And how is that power factor calculated is purely dependent on what kind of electrical devices we use at our home. For example, you're using fan driven. Okay. So in this fan, what are all the devices you think you will have? Passive elements. You will have resistance, you will have a capacitor. And the capacitor, these electricians call it as condenser. Or cylinder shape, you will have a whenever your fan stops working, the first thing they will check is condenser. Condenser is nothing but a capacitor. Okay. And third is you will have a coil inside, and the coil on the inductor. So you have a resistive element and reactive elements like capacitors and inductors. All those three put together is what you have. We learned something called as RLC circuit. R, L, and C, which are connected in series. Not necessarily they need to be connected in series always. In your syllabus, it is restricted to series because if you go beyond that, it will become complicated. You need to know more math. Another it is not given. Okay. Based on whatever device is offering the resistance to the amount of current that is flowing, this value of power factor, you can observe it keep changing. If at all you have an opportunity to check it, you can check it. For knob, you can press that knob and see, but do it with a supervision. Just because I do it, okay. Don't do that. You can check it. If you go closer, you can see it is slowly keep changing. And the change, one of the factors you can see is power factor. The significance of it, I'll tell you. So the reason why I showed this is whatever you're learning in this chapter, right? It is a completely application based. It's not like theory, that's not the scenario. Are you able to understand? So you're able to relate at least some ideas coming out of the parameters that are given there? Yes. So this is the reason. The significance of the power factor, maybe I'll explain it in some other class. So the energy input per it is measured in water. You need to convert it to kilowatt hours, multiply it with 10 power minus 3. So everything is there. But this is not how generally a digital meter looks like. Okay. So, but outside your house, you will have a small green color display that is there with different kinds of knobs. You can see only one value at a time. You can either see voltage or power factor or current or energy. Okay. So just have a look. Maybe you'll understand. Okay. So this is all about the devices that we discussed today. In the next class, we will see an effect called as resonance. Then I'll explain you how to calculate the average power and power factors. Last there is one device called as transformer. Actually, transformer are not given. which is outside your house. So you get time interest in the pudding. This is how a transformer looks like. You would have seen outside your house, no? Very transformers. Those are all bigger ones. This is also called as a transformer, which is used for electronic components. Now, why I bought this is I have LED lights. Okay. So to that LED light, I need to connect an adapter. So LED light requires somewhere around 5 to 12 volt now. If I directly take that LED light and connect it to this, so first thing you can see is it will burst on your face. It has happened also. Okay, one of the guys, he didn't tell me, he just put it inside, it burst also. Okay, that will happen. So 12 volt when now, what are the voltage you are getting from here actually? 220 to 240, right? First, you need to bring down that value. Yes, you need to bring down the value now. You need an intermediate device like this, which is a transformer, which will actually step down the voltage and give it. For example, it is given here. Input is 110 to 240 AC. 110 is generally in the side of US. So in US, the voltage RMS value is 110. In our country, it is 240 volt. Another it is given as 110 or 240 AC, and output will be 12 volt DC. So input you are giving an AC, and output you are getting DC. So transformer is called as rectifier. About rectifier, you learn in a chapter called semiconductors. Okay. The best example that you can think of is your mobile charger. What will happen if you directly connect it to 230 volt, it will burst. Okay. First, the charger inside it will have a transformer which will step down the voltage, and then it will convert it to DC form and give it to your device for safety purposes. You would have seen these mobile phones bursting during charging and all. On the charger, leather defect or if there is some defect inside the materials which are taking the charge inside the phone, only this will happen. There was a failure model also. I think Samsung had the 10 series or something. In this series that constantly used to burst. When you go to airports also, they were asking you don't have a power bank with the carry-on package. These are all the reasons. Okay. So whole world is connected. You have to understand the real-time application. So having this in mind, if you have interest, you can go through transformers and come before the class. You'll understand the theory which I'm going to teach. Any other doubt? That's it, right? So those who are online, any doubt, guys?
Sir, is there AC circuit with only inductor and capacitor?
AC circuit with only inductor and capacitor, it's called as an oscillator.
Okay, sir.
So you will not connect a battery.
Okay.
Application because next class.
Okay, sir.
Yeah.
Thank you, sir.